First of all, I am currently a senior technical evangelist on the Windows Azure evangelism team. So we have about, I would say, 10 people that covers various topics, and some of them have already presented at this particular user group. I think Scott Klein has previously covered Windows Azure databases, and we also have folks covering some really new and exciting Microsoft technologies in Windows Azure, or our Microsoft Cloud technology. That includes mobile services, being able to connect your devices such as your iPhone and Android phones and Windows 8 tablets to the cloud. And also we cover other scenarios such as line of business applications, virtual machines, or infrastructure as a service, and other topics that might interest you. So today, my topic is on Windows, running big compute on Windows Azure. So we will have a couple of, let's see, let me click on next. A couple of different topics. One is the Microsoft HPC project and the history of it. And then when I talked about the latest release of Windows HPC Pack 2012, which includes a on-premise server HPC Pack and also a product called the Windows Azure Scheduler, which allows you to basically perform resource scheduling on Azure itself without the actual server components. And then I would like to discuss a very exciting development on Windows Azure, which is the brand new HPC hardware in Windows Azure. Some of the SKUs include 120 gigabytes of RAM, which is quite a bit for all your big compute needs. And also look at the roadmap and future discussions. So at the end of the session, you'll probably be able to understand specifically on Windows Azure compute-intensive workloads, and also perhaps get some ideas to take some of your older compute-intensive applications and teach you some new cloud tricks. And then we have a few demos of some of the older HPC applications that I've developed, as well as ported to a modern, using a modern web interface. So first of all, let me give you a brief overview or the history of the Windows or Microsoft HPC team, so also known as the Big Compute team. So they started these projects in about 2004, and the first version they delivered was on Server 2003. What it did is allows you to run MPI or message passing library type of applications, or very much scientific related applications to use many nodes in a large cluster configuration. I think that at that time it was supporting up to 200 nodes or so, and then we released version 2, which was 2008. That's when I joined Microsoft, and that version supported up to 1,000 nodes in terms of being able to configure and manage these machines. And I think we actually at the time built the world's top 10 machine in China, which allowed us to have, I think it was 32,000 cores to be able to run simultaneously. And we recently actually ran a large simulation in Windows Azure with 50,000 cores, and we haven't even gotten started with the experiments yet. So there's a lot of exciting new development in large compute or big compute at Microsoft. And then we started supporting Windows Azure since about 2010. With our first version supporting, I'm hearing a little bit of echo. Let me actually mute someone here real quick, see if that helps. Yeah, that definitely helps. Apologize for the echo sound there. So we supported a version, I think it was SP2 of Windows HPC Server 2008. So that particular version started supporting something called Azure Burst, which allows you to connect or simply add Azure nodes to your Windows HPC cluster to be able to burst into the cloud. So that's actually the first version. And then later on, we recently released a version, which was in November, That was Server 2012 pack to start Windows Server 2012, and be able to allow you to connect to Windows Azure nodes as well as Windows 8 as a client to be able to do cycle stealing type of work. And the team actually moved from Server and joined Windows Azure team in summer of 2011. So meaning that we are entirely in Windows Azure team, so be able to support these large compute scale type of workload for our customers. So I just want to very briefly describe what big compute is. So big compute is really about taking an application that perhaps runs too slow or a single computer aren't be able to handle, and split the work up and move them into multiple machines to be able to do. So as in the 90s, people started building these really large Linux clusters. I think the world's largest one is now the machine Jaguar in Oak Ridge National Lab. I think it has in the orders of almost 1 million cores. So that's in the extreme in terms of government-sponsored projects that are or really large institutions that being able to afford hardware like that. So in terms of the rest of us, so small universities or maybe companies, that these institutions also started building small clusters. So a typical one is about 16 nodes, meaning that you have 16 computers clustered together to do a lot of work. So in 2006, when we first released our product, there's a lot of institutions started using that as their main compute resources to be able to manage a large cluster. So I also would like to call big compute as something called no idle computing. So meaning that you're trying to resource manage your investment so that it's not doing idle computing. So it's not just simply sitting there. And this applies really well in a cloud scenario where you can simply go spin up a cluster in the cloud and then turn it off when you no longer need it. So there are two important aspects of this. One is resource management tool that allows you to monitor and manage resources for your cluster, and the other one is a batch scheduling tool. So basically, you may have lots of users and you may have lots of applications that are competing for resources. So you may have to schedule them or queue them up so that they are using the resources efficiently. So how does Windows Azure extend high-performance computing to the masses? So the development of Windows Azure or cloud computing in general has started to provide businesses that don't necessarily have access to large clusters or don't necessarily want to build a large machine and perhaps only use it once or twice during the year. So, for example, one of the insurance company that we work with, they tell us that only around hurricane seasons would they actually be using the compute for maybe, I would say, 3 months out of the year. So the rest of the time, the compute clusters are simply turned off or not being used. So that actually end up costing a lot of money because you have to maintain a full staff to be able to do management on your cluster, and also you have hardware and also real estate. It's nowadays for a lot of these financial institutions, it's more about real estate, not being able to have the power and the hosting facility for these large machines. So that becomes a huge problem for them. So cloud is what a lot of these large businesses and even smaller businesses are very much interested in. Access to large amounts of compute resources. On Windows Azure, you can get up to 320 cores in a small subscription, as that is my subscription. And for people who really want to use large amounts of resources, such as our testing team, they use up to 50,000 to 100,000 cores easily when they do scalability testing. And also, this is a pay-as-you-go model, as I said. If you use your cluster only a couple of months out of the year, then you only care to pay for those, and then it ended up saving you lots of money. So here are some typical workloads that need big compute. Digital rendering. So, we actually have been working with Pixar and a company called Green Buttons. So they have been rendering real movies that are actually going to be published using Windows Azure. So digital media rendering, and it's also very much embarrassingly parallel, which I would explain later. What it means is that every single unit of work is very well encapsulated, meaning that perhaps each frame of these movies are rendered independent of all the other frames, meaning that the work can be easily parallelized out and be able to utilize many cores in parallel. So financial and insurance risk calculation. This is also one of those scenarios that are widely used. And in fact, we have a demo later today using SignalR and also the HPC scheduler to get some real-time calculation for risk management. And then engineering, modeling, and simulation. So this is the traditional compute. So they generally tend to use these linear algebra libraries to model a physical system. So for example, so there's a lot of CFD simulations or computational fluid dynamics simulations that are used by car manufacturers to make sure that their car models are efficient. So those type of applications tend to require very fast interconnect, which our new HPC SKU in Windows Azure will be able to provide with 120 gigabytes RAM and 16 cores and some of the best processor that's in the industry. And also computational life science, probably one of the most scalable type of applications. So I just talked to folks at the NCSA. They have a new machine called I think it's called Blue Water. That machine has 370,000 cores. So they are running, able to use the entire 370,000 cores running one simulation. So namely a computational code called NAMD for molecular dynamics computation. And then Earth and Science. Earth and Science are also very important. I actually have a weather simulation as a portal to show you at the end of this presentation. And also data analytics. Data analytics involves Hadoop and other interesting big data computation. So I like to think of big data being part of big compute. It's a subset of big compute, where instead of using lots of CPUs, you end up using the hard drives on your machine. So for example, Yahoo tends to have these really large Hadoop clusters, which have 24 disks per spindle per node. So instead of emphasizing on processor power, they emphasize on I/O-intensive applications. I will probably be doing a big data presentation in the coming months. But for this particular presentation, we'll focus on only big compute, which is only CPU compute intensive type of workload. So here is an illustration of something called an embarrassingly parallel application, which works great on cloud and, well, especially in the cloud, on large clusters and especially on the cloud, because each unit of your work is not dependent of each other, meaning that you can spin up as many processes as you like. So we mentioned a few of those type of applications. Digital rendering is one of the largest, and also insurance computation. So people could be computing different portfolios on each of the processes independently. There's, as you can see, there's absolutely no communication or very little communication between all the different application logics that runs on each of the compute nodes. Here's a very interesting example. This is actually an engineering application, but on the other hand, what these guys are doing, it's a company called Design Optimal Solutions. So what they're doing here is doing design optimization. So they're simply varying the parameter on that elbow-looking device, which is actually an exhaust pipe. So trying to maximize the efficiency of this device by varying the geometry of this device. So by changing the mesh a little bit and be able to come up with, let's just say, 5,000 slightly varying variations for the design, they are able to save 3%. They were able to achieve a 3% efficiency improvement. And I think it took them maybe 60 engineers at Ford to be able to do the same. But unfortunately, they were the human beings were only able to do about 0.6%. So this is a very typical workload that people run, which is to change the design slightly and go ahead and run variations of the same design and look at the end results to see which configuration works the best. And each of these problems are relatively small, but you run thousands and thousands of them to come up with an optimal solution. So here's another example. This is also an engineering application. It's something called MPI. It's been around for, I would say, 30 or 40 years, and many of the senior leadership at Microsoft, originally, many of them from Microsoft Research, invented this protocol, and folks like Tony Hay have actually written the spec or proposed specs of this many years ago. So these type of applications are essentially solving these large linear systems or matrices. So nowadays, you probably wouldn't write anything using MPI. You're probably using a numerical library that sits on top of MPI to be able to do the computation. So these type of applications require specialized hardware. This is where these large clusters at national labs tend to be able to afford, which is extremely large, good interconnect. Here's actually a simulation that we ran, and it's simply showing you the precipitation, or actually it's a weather application that I ran, and showing you the precipitation over a year around the country. As you can see, it does rain a lot in Seattle, and especially in Seattle area, it just rains a lot. So that's why I have moved out of Seattle, and I have I'm now actually based in Boulder, Colorado, which is a lot drier and has a lot more sunshine. But just don't tell that to my colleagues. So here are the some of the new hardware that's coming up. One of them is a 8-core configuration with 60 gigabyte, and the other one is 16 cores with 120 gigabyte instances. So all of these are actually virtualized. That's actually the amazing work that Microsoft's server team has done. So this is the RDMA work they have done to do the virtualization, meaning that the interconnect as well as the CPU are extremely efficient, even though they are virtualized. I've actually done some performance tests on them, and the most recent LIMPAC run they've had is actually running at 90% efficiency, which is considered very good without virtualization. So with virtualization, we're able to achieve extremely good performance on these hardware virtualized. So the point is that there's a lot of work that has been put into this, and it will be really fantastic for any type of scientific engineering applications to be able to run on our cluster when, the new hardware when it becomes available. And we are going to have, probably pre-release and coming up in the next 3 or 4 months. So if you have any questions, please do feel free to type them in, and I'll answer all of them at the end of the session. The third type of applications, we went through something called embarrassingly parallel application, which is the simplest thing to run. In fact, a lot of cloud compute hours are run using that. So there's no communication in between. And then the second type of application, which is very tightly coupled, meaning MPI type of application, are the traditional HPC applications. So those applications tend to use a lot of CPU, and they tend to chat a lot. So you need these very expensive interconnects to be able to run those. And the third type is becoming even more popular these days. It's called the IO-intensive application. So mostly people are aware of this through something called big data. So Hadoop runs that way. So it's very similar to HPC applications where you're clustering a large amount of machines together to be able to do the work. But in this case, you are maximizing on the I/O capabilities of these clusters, and you'll probably use a relatively simple paradigm called MapReduce to be able to run your application, meaning that you would actually take your code and map them onto the nodes that actually have the data on them. So it's a distributed system with a distributed file system for you to be able to run data-intensive applications. So we're not going to discuss that so much today, but I'll probably have a session in the coming months to discuss Hadoop and Microsoft. So this is actually the website for Microsoft HD Insight, which is our Hadoop on Windows Azure offering. And you can go to www.hadooponazure.com, or you can simply search for HD Insight. There's an invitation link on there, and you're welcome to sign up for a free three-node cluster to be able to start running some of it if you're interested. And also, so the focus of today's topic is really about HPC servers. So we're not going to go into too much of the big data. But if we do have time at the end of the presentation, I might be able to show you what it looks like and give you a very brief introduction. So let's go back to HPC server. We went through the three different types of application models, which is embarrassingly parallel, tightly coupled, and also data intensive. So let's talk about how these things are being managed by the Windows HPC Server Pack. So first of all, the HPC Pack consists of job scheduling, which allows you to be able to prioritize workloads that are submitted by various users. And we also have cluster management, be able to show you which machines are up and running and their CPU utilization, essentially a monitoring tool. And this is connected to Windows clients. You can actually have Windows 7 and Windows 8 machines connect to Windows HPC Server, or a Windows Server machine installed with HPC Pack. And then you can also connect Windows HPC servers to it to be able to do more interesting workloads, because HPC Server generally supports these InfiniBand and all those specialized hardware better. And of course, you can just right-click and add a bunch of Windows Azure nodes, which are running in the cloud, if you run out of resources on-premise. So this is what this product is all about, being able to manage large amounts of cluster, large amounts of node resources on-premise as well as on Windows Azure. So here are some of the use scenarios. One is that folks might want to just simply run a cluster on-premise, meaning that you have one head node which controls a bunch of server nodes or client nodes, and you're happily running and you don't need any resources in the cloud. So that's the traditional way of running things. The second way of running it is saying, okay, I do have a cluster on-premise, and you can run and control a bunch of nodes on-premise as well as adding nodes to the cluster. And the third configuration is simply saying, okay, I don't have much resources on-premise, and I only want to use the nodes that in the cloud. So you can only simply add nodes from the cloud. So here are what we offer in terms of features on these on-premise versus the cloud. So obviously you need the parallel runtime. So for example, the MPI library, SOA or SOA, service-oriented architectural runtime, and you may need resource management. And on Windows Azure, you probably need pretty much the same thing, except that you need special software that connects and talks to Windows Azure Fabric, so be able to manage and provision hardware resources in the cloud. So here are some. Here's the running a diagram of running cloud applications in Windows Azure. So first of all, we support applications hosted entirely on Windows Azure now. So meaning that you would have no on-premise nodes at all. So that is the Azure Scheduler that I will discuss and show you an example of. And application is accessed from rich client on-premise portal and web applications. So what's new about the cloud is not simply being able to utilize a bunch of resources in the cloud, but also be able to access those resources much easier. So one of the interesting things that people tend to do is to have their rich client, meaning that their client may have 3D rendering connects onto Azure resources or the compute resources. That's one way of accessing either local resources or remote resources, and then using a portal. So essentially you have a website which allows you to start running these long, very compute-intensive workloads using a portal, and then finally using a web application that has been customized for that. And also there are multiple business models for our customers for selling their HPC application. One is selling it as a package and be able to connect to Azure, which the customer pays for and the customer manages. And the other way is to simply provide HPC as a service. Simply allows you to connect to a portal, and you don't actually buy the software or install the software. You run everything through a web portal or as a service in the cloud. So those are the two main business models that people can utilize the cloud resources. And the scheduler runtime support includes parametric sweep, which as I said, very much the embarrassing parallel application. You send it 1,000 tasks, and it farms it out to the resources that you have, either in the cloud or on-premise. SOA, which allows you to keep a lot of things in memory and be able to call these services relatively quickly. So for example, banking and insurance might want this model. So if I want to do a pricing of a security instantly, I may simply click on a Excel spreadsheet and be able to get my calculation back in real time, even if the entire job has not finished. And then finally, MPI, as we discussed, mostly for matrix solvers and these scientific applications. And of course, on Azure scheduler, we don't necessarily need a head node. So it's simply doing scheduler service and not necessarily the admin service, because that's taken care of by Windows Azure for you. So in order to build a scheduler-enabled deployment, you need Azure subscription, obviously, and your application, which you have to package, and it's a pretty straightforward process. Essentially, you're zipping it up and copy it into Windows Azure, and you have to construct a CS package. That's just a tool that you can use from Visual Studio, and then you can customize simply saying how many cores you need and deploy that through Visual Studio or through on-premise package that the developer gives you if you don't have Visual Studio. So this is how Windows Azure Scheduler works. It has an application front end, and we'll show you an example very soon. It consists of the HPC job scheduling, which is resource management, and then you have a bunch of compute nodes sitting in the background, and that can do a bunch of work, right? So, and then finally, here are the features of big compute, and then soon we will go to demos. One is on-premise, you have the hybrid HPC solution, which essentially allows you to run workloads that are sitting on-premise as well as work that are running in the cloud. And job scheduling and runtime services, those are essentially what you need to be able to run your job. And those are libraries and also services that we provide you on your on-premise and the nodes that are actually doing the computation. And soon we would have, as I said earlier, we'll have premium hardware, which will have RDMA networking, and we'll have remote visualization and workflow. So a lot of that work is currently in progress in the future works. So let me actually show you how very quickly you can actually create a cluster. So this is something called the HPC Azure Job Scheduler. So what you can do is you can go download that package, load that up in Visual Studio. It's essentially a template that allows you to create a front end, which would be a web portal, and then a head node, and then a bunch of worker nodes that you can add to it. And then you can add your Azure sample services. And then as soon as you configure how many nodes you want, you can deploy that. In terms of the work, you can simply attach a new project and add the computation or the executables that you want into the Visual Studio project and use the configuration panel to deploy your work. So that's one way of doing that. And I also have ways of using PowerShell and other deployment methods. Yeah, that's right. As it says, I have PowerShell available as too. And if you look on my blog, you'll be able to see a lot of that. The other interesting configuration is using a rich client. So this is actually an OpenGL client that allows you to simply right-click and say, I want shared memory, cluster, or the cloud. So this is a company called SimsGate, which I work very closely to help port a piece of code called OpenFOAM. This is essentially doing a fluid computation of fluid dynamics. So this is basically a race car. As you can see, there's a vortex at the end. So what we did is essentially running this rich client on locally and be able to select Windows Azure in the cloud and providing with subscription information and just simply click on compute, and it will upload the code to Windows Azure and do the computation and download that transparently. So a lot of that, detailed information can be found on my blog, or you can definitely contact me through my email if you want to know more about it. And there's also a bunch of open source ecosystem. So a lot of these tools actually work very well on Windows. In fact, I would be able to go on a Linux machine and use a cross compiler from the MinGW team. MinGW is a compiler that allows you to compile very much any Linux source code into Windows. So a lot of these HPC applications are actually cross-platform. So people run this on Linux. So we have tools that allow you to simply do a compile on Linux and take that executable that you compiled on Linux and run that, being able to run that on Windows machines, meaning Windows Azure. So it's actually a very cool set of tools that we're providing to be able to do large computation. So let me actually show you one of the examples of Windows Azure as a service, and I have actually a live demo of that. So this is a piece of code from National Weather Service called WRF, or Weather Research and Forecast. What it does is it does a forecast of up to 3 days for you. So what we do is that we can run a one city 180 kilometer by 180 kilometer square and run that in an extra large VM on Windows Azure. And let me actually show you how that works. So the first thing I want to show you is that the Windows Azure Portal. The Windows Azure Portal is very much straightforward. It's really designed by excellent UI designers that we have. So on here, if I click on Windows Azure, as you can see, there's like a lot of things that I have in my account, a lot of things that are going on. So what you can do is there are websites. Websites are extremely easy to be able to deploy. It's simply allowing you to FTP a bunch of files onto websites or use Git to publish a website. And then there's virtual machines. Virtual machines actually mean that you provide your own machine. So you use your own machine image. It has Linux virtual machines, and we also have Windows virtual machines. As you can see, I actually have a Linux machine running here, and then I have a HPC Burst, which is a Windows Server 2008 machine. So these are all strictly VM. And also we have something called cloud services, which means these VMs are provided to you by Microsoft. They'll be patched and done and worked on by Microsoft. You don't have to worry about anything. So this is actually I would say the future of cloud services, which means you don't administrate your own machines. You simply say, I want 15 machines, here are the startup script, and here's my program, go run it. And the weather service that I'm showing you here is running in the Windows Azure Portal. So currently, I actually have 44 cores running. So for this particular service, I have 44 cores. So in the composition of this particular service, I have 5 extra large instances. Those are doing actual compute. And then I have a head node, which is the, simply one medium, which has 2 cores, and then a medium front end. So let me actually show you how the process runs. Let's see. So let me see where it is real quick. Here's the weather service. So if you go to weatherservice.cloudapp.net, you will be able to see the live service running. So I actually have a little queue that shows that there are currently 2 services running. Apparently someone has submitted 2 of these jobs, each of them running at 61% and 63%. And you can run a new forecast. So if I want to run a forecast for, this is exactly where I live, but if I want to do one for San Jose, I can just click on it and say San Jose, right? And simply say save, and then it would be able to go ahead and allocate resources on the cluster and be able to run that for you. So let's actually look at the cluster management portal. So this is actually all done entirely in a web portal now. So if I click on all jobs, as you can see that there's 2 running. Those are the 2 that I showed you earlier. There's 2 people that submitted jobs earlier. And also, perhaps my jobs. I don't have any right now. And if you look at the heat map actually shows you all the jobs that are currently running. So there's using compute node number 1 and number 3. Those are the 2 jobs that are currently running. We submitted one. And of course, it's going to take a little bit of time for it to actually come through the system. So I essentially have a web front end and a job submission mechanism, which is simply a PowerShell script that submits a job to this queuing system. And then this queuing system manages the resources for me. So I can actually prioritize and do all kinds of interesting things with the resources that I have that I spun up on Windows Azure. And of course, you can run other types of applications as you wish. So the second demo, which I like to show you, and in fact, let me go back to my slides real quick, is that this is actually a look at the actual web portal with all the screenshots. So the second one, which I want to show you real quick, is a commercial simulation that we're running right now that does computation for, see if I can find this application. There we go. So I can go back to my portal. So this particular application does a Black-Scholes sampling of large simulations that are simply running in Windows Azure. What it does is it uses a solar model, which means that as you're getting your results back, it's not waiting for the entire batch system to actually happen. So what I can do is I hit uniform data set and hit run. As you can see that the calculation, certainly it says uncalculated, but it uses something called signal R, which allows the real-time WebSockets communication to communicate to the back end instead of waiting for days for results to come back. As you can see that some green banners that are showing up. So it's finishing the computation as it's coming back from the system. So this is using the SOA model. You can also connect it to it using Windows Microsoft Excel to be able to do the computation. And so this is the Black-Scholes model, which shows the sample data is very much fitting well with the actual Gaussian distribution, or essentially a random Monte Carlo distribution system. So let's actually go back and look at the heat map again. And as you can see, I probably have all jobs. I may already have one running. So as you can see that I have 4 of them running. So apparently one of you may have submitted a job just now. So you can see I have 4 of them running now. So this is for the previous weather simulation. And other interesting things you can do. And you can use go to the gallery and you can show all the forecasts we've actually done in the past. For the various countries, and also I have a really neat little way of showing what work has been done in the past. There's a little timeline, as you can see, and if I don't need the resources, I can spin them down. But if I do need the resources, I can run multiple large simulations and spin up to for my subscription, I can spin up to 15 large extra large VMs to be able to do the actual compute. And at the end, you can actually show them in a map. All the simulations will actually run. This particular service has been running for about 9 months. So it's very different from your traditional, okay, run a bunch of code and come back to it, share the results. So the result is permanently shared through this web service. And at the same time, my service has been running for 9 months, which means Windows Azure, I'm still using the same 9 nodes that are currently running, meaning that it's extremely reliable, has not been going down for the entire time. So we've run about 1,000 simulations, actually 1,400 simulations by now, and we have about 8 million to 10 million objects because the simulation results actually get saved in the blob storage system. And at the same time, we have people that will be able to collaborate and look at the data they've actually created on these type of simulations. So of course, this is just simply a sample that I built using old Fortran code that you run, and probably only 5 to 10 scientists around the world that really understand it well. But being able to use all the technologies that Microsoft provides, including web technology. This is an MVC, Microsoft MVC application, including Bing Maps, as you saw earlier, and also including our big compute technologies running in the background to be able to make a service that goes from simply Fortran code that's sitting in somebody's drawer to a service that is constantly running without much effort having to maintain it. And I don't have to patch the system because I'm using platform as a service, because all the nodes that I spin up are managed and provisioned by Microsoft. Let's go back to our slides real quick. I want to go back to some tips and tricks. So the first thing is that the first thing to make your application adapted for the cloud is to hide the cloud from your users. So providing a transparent experience is extremely good, because the users don't really want to manage an application that he has to understand where the storage system is, how to provision the machines, and how to essentially pay their bills. So I think that would be something that makes it much easier. Essentially, somebody goes to a portal, run the simulation, get their results back, or somebody runs an application on your desktop, select cloud as a resource, run the application, gets the results back. So that would be the ideal type of application for the cloud for big compute. And for the second tip is that netting your data transfer from on-premise and the cloud will be essential, because the bandwidth is always going to be very much limited. But luckily, our networking has gotten so much better these days. Even from home, I can transfer 500 megabytes of data to the cloud within 10-20 minutes. But at the same time, it's not going to be as fast. Essentially, keeping all your data in the cloud is the best practice. And then for CPU-intensive jobs, it's probably the most economical things to run on Windows Azure or any other cloud providers. And finally, be creative and really focusing on what you can do on the cloud today, rather than what you cannot do. So, for example, I currently don't necessarily have the 120 gig RAM machines up and running, but I can design applications for that now, and we'll have that in a couple of months. So currently, you can use the current cloud resources to design your application, and then simply reprovision and utilize these larger machines when you need them. And I also have some resources that you can go to. So I have a blog, which is blogs.msdn.com, HPC Tracker, which explains a lot of things regarding to HPC and also HPC big compute and also big data. And we will, and I will be updating it as more services become available. And also, I had an old paper which talks about application models and data considerations. Essentially, shows you how to manage the data properly, how to synchronize them properly, how to be very efficient, and how to manage your data resources. So that's a good paper to read. And I think we will be making these slides available for you. And also, there's the latest version of Windows HPC Pack, which you can download from download.microsoft.com. And you can install it on your server. It's absolutely free. It used to be an actual paid product. Now it is absolutely free. And also, you may need to add some cloud resources, meaning Azure resources. Now we provide a free trial. And you will need a credit card, but there is a specific button that until you actually say, charge us, nobody, your credit card will never be charged until you specifically say that you want to use more resources. And also, I have some Azure Burst samples, which you can play with, and you can try that specific link. And of course, if you implement your big compute solution, please do let us know. The interesting thing is that big compute turns out to be the largest consumer as a single type of application on many cloud services. So because this is easy to run and it's much easier to be able to deploy and port to the cloud. So not as difficult as in line of business type of applications. So there's a lot of people that are currently using cloud resources, the big compute. So there's opportunities for you for consulting, and there's also opportunities for people who have these big compute codes to be able to save money. And thank you very much for paying attention to the webcast, and also and I'm ready to answer questions. If you type them into the chat window.